Sound of very faint, low, rumbling thunder, subtly layered under ambient space sounds, then fading. Imagine standing on a distant, impossibly large world, a world where storms rage with unimaginable power. For centuries, our ancestors, peering through early telescopes or simply gazing at the bright point of light in the night sky, must have pondered the secrets held within Jupiter's swirling, chaotic atmosphere. They saw bands and spots, ever shifting, ever changing, and perhaps they dreamt of lightning, bolts of raw energy electrifying that colossal globe. But it was just a dream, a theory born of imagination, for how could one confirm such a thing across millions of miles of empty space? The idea persisted, a whisper among astronomers through generations. Surely, the largest planet in our solar system, with its turbulent clouds and immense scale, must harbor electrical storms. It was an educated guess, a compelling intuition. Yet, for all their wisdom and keen observation, definitive proof remained elusive, hidden behind the vast cosmic curtain. Then came a pivotal moment, a giant leap in our understanding. In 1979, the curtain was finally dramatically pulled back. NASA's Voyager 1 spacecraft, a testament to human ingenuity and relentless curiosity, hurtled past Jupiter. As it made its historic flyby, it captured data, images, and signals that finally confirmed what humanity had long suspected. Yes, Jupiter indeed had lightning. The ancient theory was vindicated, a quiet triumph for centuries of observational astronomy. But as with so many moments of scientific discovery, the confirmation brought with it a new, even more intriguing mystery. Voyager 1 didn't just confirm an old suspicion, it unveiled an entirely unexpected twist. The Jovian lightning, those magnificent electrical discharges, weren't appearing where most of us might intuitively expect them. They weren't zinging across the planet's vast midsection, its equatorial belt, like the familiar electrical storms on our own Earth. Instead, Voyager 1 found that Jupiter's lightning was almost exclusively confined to the planet's poles. Think about that for a moment. On Earth, our lightning storms are most common and most intense around the equator, where the sun's warmth is most direct, fueling towering thunderstorms. But on Jupiter, it was the exact opposite. The poles, those perpetually shadowed and often thought of as calmer regions, were where the sky truly ignited. Why did lightning bolts avoid Jupiter's midriff like the plague, opting for the far reaches of its polar regions? This became one of the great atmospheric puzzles of our solar system, a question that lingered for decades. It took another extraordinary mission, another intrepid spacecraft, to begin to unravel this enigma. In recent years, the craft Juno, a marvel of modern ingenuity, embarked on its own daring ballet around Jupiter. Juno, unlike Voyager, was designed specifically to orbit and study the gas giant up close, repeatedly diving through its powerful radiation belts. And it was Juno that finally provided the crucial insights, identifying the subtle yet profound reason why lightning never zings the planet's equator: heat. To truly understand this, let's briefly consider how lightning forms on Earth. Our planet catches the brunt of the sun's warmth around the equator. This direct sunlight heats the surface, which in turn warms the air above it. Warm air is lighter, less dense, and so it rises, carrying moisture with it. This process, known as convection, creates powerful updrafts that form towering thunderstorms. Within these clouds, ice crystals and water droplets collide, generating static electricity. When the electrical charge builds up sufficiently, zap, lightning strikes. It's a classic recipe for terrestrial thunderstorms. Now, here's where Jupiter's peculiar atmospheric dynamics come into play, essentially reversing this process. Once sunlight reaches Jupiter's equator, making that vast region incredibly toasty, something counterintuitive happens. Instead of fueling robust, rising plumes of warm air, the immense power of the sunlight stabilizes the world's upper atmosphere in a unique way. It creates a kind of atmospheric cap or lid that suppresses the very rising warm air that lightning needs to form. Think of it like trying to boil water with a heavy, perfectly fitting lid on the pot. The steam just can't escape and rise freely. For this reason, Jupiter's equator, despite receiving the most direct sunlight, remains relatively calm when it comes to electrical storms. There's no significant upwelling of warm, moist air to drive the thunderclouds. But then we turn our gaze to the poles. Here, the atmospheric conditions are dramatically different. There is no such stabilizing effect from direct sunlight. Instead, the poles benefit from heat generated from within the planet. Jupiter is still slowly contracting, a process that releases enormous amounts of internal heat. At the poles, where there is no atmospheric stability to counteract it, this internal heat pushes warm, less dense air vigorously upward. This creates powerful convection, much like Earth's equatorial regions, but driven by an internal furnace. It's this rising hot air, laden with moisture from Jupiter's deep atmosphere, that fuels the colossal thunderstorms at the poles, allowing lightning strikes to freely ignite those distant, magnificent skies. So, the mystery of Jovian lightning, once a centuries-old speculation, then a bewildering paradox, has slowly, patiently been unveiled. It's a testament to our persistent curiosity and the incredible journeys of our robotic explorers. Jupiter's lightning is not merely present, but profoundly unique, a mirror image of our own planet's electrical dance, where the heat that drives the storm comes from within, and the sun's warmth, surprisingly, brings calm. It reminds us that even in our own cosmic neighborhood, the universe continues to hold surprises, inviting us to look closer, to question deeper, and to never stop exploring. What are your thoughts on this incredible planetary reversal? Does it change how you see the gas giant? Share your insights in the comments below. And if you'd like to journey deeper into the cosmos with us, consider subscribing and joining our growing community of curious minds. Until next time, keep looking up.